So when we get 0 over 0 from a limit, or infinity over infinity, which we haven't seen those before, but you can get that as well, we had to use some tricks. To manipulate the functions into something that we could do a direct substitution. And at that time we didn't know derivatives, so we couldn't use this on it. However, once we know derivatives, we can use L'Hopital's when it's an indeterminate form. But that only works when we get 0 over 0. If you get a number over 0, we got to use our other methods. If you get 0 over a number, you got to use our other methods. Okay, if I direct substitute a -1 into this function, I'll get 2 minus 2 in the numerator. Well, that's 0. And I'll get -1 plus 1 in the denominator. That's 0. That's an indeterminate form. So before, we would have factored this. And if I factor out a 2, then I'll have x squared minus 1, which is the difference of squares. We would simplify that, and we would say it's the limit as x goes to -1 of 2 times x minus 1, which I can now do a direct substitution on. If I plug a -1 in there, we're going to get -4. So that one has a method for us to figure it out, but what if we don't have a trick? If I plug infinity into this, we're going to get e to the infinity over infinity, right? That's infinity over infinity. That's also an indeterminate form. And we don't have a trick for that one. But if we use L'Hopital's, we can figure it out. L'Hopital's says if the limit of a rational function results in an indeterminate form, so 0 over 0 or infinity over infinity, then the limit can also be found by taking the derivative of the numerator and the denominator. Right? So back when we first did limits, we didn't know derivatives. We couldn't do this. But now that I know derivatives, we can use this to do the limits. So let's go back to those first two examples I gave you and do it this way. So the first one we looked at was the limit as x goes to -1 of 2x squared minus 2 over x plus 1, and we factored it, and we saw it was -4. Well, and we also saw it was 0 over 0 before we did that, so that means I can do L'Hopital's on this. So we're going to say it's the limit as x goes to -1 of the derivative of the numerator. What's the derivative of my numerator? 4x over the derivative of my denominator, 1. And so what do we get when we plug that in? -4. Okay, now the one that we didn't know how to manipulate it was the limit as x goes to infinity of e to the 2x minus 1 over x. And we got infinity over infinity, indeterminate form. So we can do this using L'Hopital's. What is the derivative of my numerator?
2e to the 2x.
2e to the 2x. What's the derivative of my denominator? 1. So what do we get when we plug in infinity? Infinity. So we've got an asymptote there, right? Nah, not necessarily an asymptote, because we're looking at end behavior. The limit as x goes to infinity. Okay? Let's try some more. Whoops. All right, same function, but different limit here. I'm looking for as x goes to 0. Now, if we plug in a 0 for x, we're going to get e to the 0, which is 1. So in the numerator, I get 1 minus 1 is 0. In the denominator, I get 0. So also an indeterminate form, right? And we already took the derivative of these just a second ago. And we got 2e to the 2x over 1. And if we plug a 0 in here, what are we going to get? 2, right? E to the 0 will be 1 times 2 will give us 2. All right? Limit as x goes to infinity of natural log of x over x. Now, as x goes to infinity, natural log of x is also going to infinity. So we're going to get infinity over infinity, which is an indeterminate form, which means we can use L'Hopital's. And we don't have another method for this function. Whoops. What's the derivative of natural log of x? 1 over x. And then the derivative of x is 1. So if we plug infinity in here, what am I going to get?
1 over infinity.
1 over infinity, which is 0, right? If I have one pizza and I have to feed 10 million people, how much pizza does everybody get? None. My pen is not writing correctly here. All right, limit as x goes to negative infinity of x squared over e to the negative x. So x squared, if I plug a negative infinity in there, I'm going to get a positive infinity, over e to the negative x. Well, e to the negative x with a negative infinity would be e to the positive infinity, which is infinity, right? So we've got infinity over infinity. We can do L'Hopital's on this. Derivative of x squared
2x.
is 2x. Derivative of e to the negative x. Negative e to the negative x. Okay, if I plug in negative infinity, what am I going to get here? I'm going to get negative infinity over negative infinity. So have we gotten anywhere? Let's do it again. What's the derivative of 2x?
2.
What's the derivative of negative e to the negative x?
E to the negative x.
Okay, plug in negative infinity and we're going to get 2 over e to the infinity. What's the answer?
0.
0. So if L'Hopital's doesn't work the first time and you still get an indeterminate form, you keep going until it works.
So that's essentially what it's for. It's just to find the ones that are like infinity over 3 and 0 over 0.
Mm-hmm.
It's going to result in 0.
So if we get negative and negative.
You put E bubble and E, that's 0.
All right, this is an interesting one. E to the negative x times the square root of x. If I plug in infinity here, we're going to get e to the negative infinity times infinity. Now, e to the negative infinity is 1 over e to the infinity, right? So that's 0 times infinity. So that doesn't appear to be an indeterminate form, does it? But if we rewrite it as the square root of x over e to the positive x, that's how we figured out e to the negative infinity was 0, is it was 1 over infinity. So then we'll get infinity over infinity. So it truly is an indeterminate form. So we can use L'Hopital's on this. And the derivative of square root of x?
1/2 x to the negative
1/2 x to the negative 1/2 over derivative of e to the x is e to the x. And if I rewrite that, with it all in the denominator, then when I plug in, I will see I'm going to get 1 over 2 times infinity. What's that going to be?
0.
0.